Hello, the purpose of this video is to give you the overview of Unit 3.3 video tutorials on gases and pressure. There were 4 of them, so we're going to just take a little bit of time to review those 4 videos by looking at the notes packet. On page 8 of the notes packet, you will see the kinetic molecular theory, which explains ideal gas behavior. And there's a couple things about the kinetic molecular theory that you should know. So they're numbered 1 through 5. Gases are made up of molecules that are extremely tiny and far apart from each other. Right, so tiny and far apart. This is really critical to the understanding of why gases behave the way they do. We'll get back to that in a minute. But this is also why gases can be compressed, because they're so far apart from one another that they can actually be pushed together in that space. Because there's so much space between them. Gas particles move in a constant straight line motion. Any collisions a gas particle makes will be elastic, so that there's no loss of energy. What elastic means is, unlike in the real world, when, like for example, when billiard balls hit each other on a pool table, the billiard balls slow down after that collision because of friction, and they slow down. But on this molecular level, this atomic level, collisions are considered to be elastic. No energy is lost, no speed is lost. Number 4, there's no intermolecular attractive force between gas particles, right there. So this is the IMAF that we talk about in class. There's considered to be no intermolecular attractive force, even though all substances actually have attractive forces, but because the distances between the molecules are so far apart that any intermolecular attractive force that exists is insignificant, doesn't even play a part. Okay? The average speed of the particles, so what we're really talking about the average speed, we're talking about the kinetic energy. The average kinetic energy of the particles is directly proportional to the Kelvin temperature. So we've talked about this before, but Kelvin temperature is a measure of kinetic energy, which is the average speed of the particles. Okay, so if a gas is considered to be an ideal gas, then we see that they will follow these kinetic molecular theory tenets. So ideal gas behavior really only exists when there's high temperature and low pressure. And let's talk about this just for a second. Okay, high temperature, what's happening when particles are at a high temperature? What's happening? Molecules are moving faster. That's what's happening. What's happening at low pressure? What's going on with the particles at low pressure? Well, there's more space between them, right? So if your molecules are going to be moving fast with lots of space between them, that's when ideal gas behavior is at its peak. The other thing that can promote ideal gas behavior is the size of the particles themselves. So small particles, especially like hydrogen and helium, they have fewer electrons, therefore they have very weak intermolecular attractive forces, which are the most ideal conditions. Okay, so let me move that in the screen there. So what do we need to do to have a gas behave least like an ideal gas behavior? You're going to see this test question crop up every now and again. To inhibit ideal gas behavior, you're going to want, of course, low temperatures. So the colder it'll be, the slower the molecules will be moving. And high pressure, the particles will be closer together. So when particles are moving slower, with less space in between, that's going to allow those it's going to allow those intermolecular attractive forces to actually take hold. And what potentially happens is, once those intermolecular attractive forces take hold, the gas is less gas-like and actually becomes more liquid-like. So ideal gas behavior just means you're trying to promote the most gas-like behavior, which is particles moving fast, particles moving and far apart from one another. All right, so moving on to Avogadro's hypothesis, which basically says you have equal numbers of particles of gas, which will occupy equal volume, the same amount of space, under the same conditions of same temperature and same pressure. All right, so really what we have here, we have three gases, carbon dioxide, ammonia, and oxygen. These three gases will have the same volume. They're both 1 liter, 1 liter, 1 liter. They're both at the same temperature. They're all three, not just both, 298 Kelvin. They're all at 298 Kelvin, and they're all at this pressure of 101.3 kilopascals. We'll talk about that pressure unit in a little bit. But these three gases, all with the same volume, same temperature, same pressure, they're all going to have the same number of particles. How many particles that is, right now you don't need to worry about that. Just that really what this means is that the math we want to do with gases can be applied to all gases. It's independently of what gas it is. That's really all you need to know, or why we need to know Avogadro's hypothesis. All right, so I guess I already spoke a little bit about this deviations from the ideal gas law, right? So the ideal gas law works well under standard conditions of temperature and pressure. STP stands for standard temperature and pressure. Standard temperature and pressure can be found on reference table A, right? So reference table A has those standard STP conditions, right? Be familiar with that little acronym. You're going to see that show up and you're going to go, what is STP? But it's standard temperature and pressure. 0 degrees Celsius, of course, which is equivalent to 273 Kelvin. Standard pressure is 1.000 atmospheres or 101.3 kilopascals. Which is the same thing as 760.0 millimeters of mercury. Old-fashioned unit for millimeters of mercury is torr. We pretty much don't really ever use that. Continuing on to page 9 of the Unit 3 notes packet, you're going to see a little section on pressure, which is defined as the force exerted over an area. And we are specifically going to be talking about the force that air, the atmosphere, exerts, and we're going to see that air pressure is measured either in atmospheres, kilopascals, or millimeters of mercury. So these conversions, PSI is a unit that you'll see whenever you have to put air pressure into your car tires or bike tires. PSI stands for pounds per square inch. But we don't really use that unit in class. So atmospheres, 1.000 atmospheres is equal to 101.3 kilopascals, which is equal to 760.0 millimeters of mercury. Note the use of 4 significant figures in all of these conversions, which really should not limit any of your calculations that you'll have to do in this class. First example, what we see here is if we need to convert in and out of atmospheres in kilopascals. Rosengarten in the text sets up his fractions not to look like fractions. He does them all in one line. I find that to be a bit confusing. I need to see the fractions a little bit, so I'm going to show you just what this conversion looks like done that way. So if we have the pressure reading of 2.3 atmospheres and we're being asked to convert it to kilopascals, the first thing that you're going to want to do is set up a conversion fraction. So in that fraction, we're going to want to have atmospheres in the denominator so that it will cancel. We're going to want to have kilopascals in the numerator. And then here is where we know we wouldn't want to put 1 up here because it's not 1 kilopascal. It's 1 atmosphere is equivalent to 101.3 kilopascals. So here what you can see is that you'll be seeing the atmospheres cancel, and that 101.3 times 2.35 is going to give you, I believe, an answer of 238 kilopascals. The next example that he shows you is 123.4 kilopascals. You're being asked to convert that to atmospheres. So again, what you would want to do is, I'm going to borrow these units from up here. This time you want kilopascals on the denominator so it'll cancel, and you want atmospheres in the numerator. So here you're going to see that you're going to have 1 atmosphere in the numerator and 101.3 kilopascals in the denominator. Of course, you're still going to see kilopascals cancel, right? So now the math is 123.4 times 1 divided by 101.3, which gives you, I think, an answer of 1.218 atmospheres, right? So those examples are laid out for you. Just, I think they're a little easier to see in this format. Moving on to vapor pressure. Vapor is a word that is used to describe when a substance has turned into a gas. A vapor is a gas, but the substance is typically a liquid at normal room temperature. So, for example, water is normally a liquid at room temperature, and so when it turns into a gas just by evaporation, we tend to call that a vapor as opposed to a gas. Just as a subtle distinction, but vapor is essentially, bottom line, it's a gas. So vapor pressure is the pressure exerted by the liquid's vapor in a sealed container. So it's the pressure, let's get that. It's the pressure exerted by a liquid's vapor in a sealed container at vapor-liquid equilibrium at a given temperature. Okay, so sealed container, no energy in, no energy out, no particles in, no particles out. There's that vapor-liquid equilibrium. What that means is for every gas molecule condensing into a liquid, there's a liquid molecule evaporating into the gas form. So this is at a given temperature. Temperature is not changing. Okay. Vapor pressure of a liquid is not dependent on the mass or the volume of the liquid. Okay. Reference table H is where we're going to take a look at that in a moment. And we've already looked at this a little bit. We were able to see that the stronger the attractive forces are between, the stronger the intermolecular attractive forces are between molecules, the lower the vapor pressure is. So we will come back to that in just a moment, right? Actually, right now. So what we are seeing here is that, I put this little graphic here. The stronger the intermolecular attractive forces, what that means is that the particles like each other. They want to be together. Okay, so that means they're going to be more likely to be in the liquid phase, which means they're less likely to be evaporating. The less likely they are to be evaporating, the lower the vapor pressure will be because there's fewer particles in the vapor phase. Let's think about this in the reverse. If the intermolecular attractive forces are weak, that means the particles don't care about being next to each other, which means they're more likely to evaporate, which means their vapor pressure is more likely to be higher. All right, so what you can see here is that substances that have high vapor pressures will evaporate quickly. They are considered to be volatile, so there's just a vocabulary word. Volatile means they evaporate quickly, and as a result, they will have high vapor pressure. So let's take a look at boiling point. Boiling point is the temperature at which the liquid's vapor pressure equals the pressure exerted on the liquid by outside forces. So essentially, the outside forces we're talking about are whatever the atmospheric pressure is. Okay, so boiling point is the temperature when vapor pressure equals atmospheric pressure. Okay, we can use reference table H to determine the liquid's boiling point. Boiling point will increase as exerted pressure is increased. Okay, so I'm just reading that right there. So let's take a moment to take a look at reference table H, which is on the next page. First thing to notice is that the scales for temperature and vapor pressure are different scales. On the y-axis, vapor pressure, each individual block right here represents 10 kilopascals, but down here, every block is 5 degrees Celsius. So just pay attention, it's really easy to kind of screw up which axis you're looking at. All right, so what we want to take a look at is how to interpret boiling point at various pressures. So let's first talk about standard pressure. Standard pressure is this line right here, 101.3 kilopascals. If you read across this 101.3 standard pressure and where it intersects each one of these lines, that would be the normal boiling point for each substance. So propanone right here, if you were to read straight down, would be a little bit more than 60, maybe 61, 62 degrees Celsius right there. The normal boiling point for ethanol is where where it intersects right here. So that would be maybe about 79 degrees Celsius. Water, of course, intersects exactly at 100 degrees Celsius, and ethanoic acid intersects at about, what is that, maybe 117, 118 degrees Celsius. Okay, so that's normal boiling point. So when the atmospheric pressure is 101.3 kilopascals, that's standard pressure, that's what the vapor pressure is, and that's normal boiling point. But of course you know that you can change the atmospheric pressure by either using a pressure cooker or by your altitude of where you live can affect your atmospheric pressure, and so therefore the boiling point changes of these liquids over those different pressures. Okay, so if we take a look at the couple examples that are here, what is the vapor pressure of blank at blank degrees Celsius? Okay, so this is how to use this table. So what if the vapor pressure of ethanol is 40 degrees C? Okay, so let's take a look at where example A is. Example A, at 40 degrees C, we find that we got to make sure we read up to the correct substance. In this case, it was ethanol, and then we can read over here to find out that the vapor pressure is somewhere maybe 15 or 16, if I'm reading that right, kilopascals. I guess Rosengarten interpreted it as 17. All right. Another type of question, what is the boiling point of some substance at a pressure of some kilopascals? So for example, what is the boiling point of water at 30 kilopascals? Start at the 30 kPa point right here, read over to water, read down, you're going to find that that's 70 degrees Celsius. So boiling point for water is 70 degrees Celsius at a pressure of 30 kilopascals. What is the normal boiling point of a particular substance? This is where you just read over at the standard pressure line that is, I believe, marked for you on table H. Okay. One of the other things we should probably recognize, and we touched on this once before, you can see here that these four substances have very different boiling points. That is, of course, due to their intermolecular attractive forces. So of these four substances, how do their intermolecular attractive forces change? So how you want to approach this is, let's think about this. Ethanoic acid has the highest normal boiling point. That means it doesn't want to boil. It takes a lot of energy to make it boil. In that case, this one right here would have to be a fairly high intermolecular attractive force to keep them in the liquid phase. Right? So over here, this substance would be the weakest intermolecular attractive force because it has the smallest boiling point temperature, and therefore it doesn't take very much energy to turn the liquid into a gas. All right, well, this concludes the overview of Unit 3.3. I hope this helped. Now would be a good time to try the Unit 3.3 problem set. All right, see you back in the classroom.